is Lutz Duembgen from University of Bern. So he'll talk about p-values for computer-intensive classifiers. Sorry.
So thank you very much, and thank you to the organizers for inviting me. I have to admit I'm not such a high-dimensional guy, as some speakers as well. This is a project which I started quite a long time ago with a diploma student, Lars Hömke, but then he switched to another subject. I went to Switzerland and we did not continue, but last year I put Bern, Wolfgang Igel and Axel Munk on board, and we continued this. So what I'm wanting to do is first of all, I want to convince you that p-values are a very interesting tool or an alternative to usual classifiers. And a second message is that whatever classifier you like to use, whether support vector machines, neural nets, or whatever, it should be possible to change this procedure into a procedure giving you p-values, as I will describe later on. And in the very final part, I will indicate some aspects of high-dimensional settings. Okay, so first from classifiers to p-values, let me briefly recall some concepts. So you have a random pair x and y consisting of an observed feature vector x and an unobserved class label y. So I'm thinking about capital L possible classes. And the goal is to make inference about this class membership y based on the feature vector x. And so a classifier in the simple setting, suppose for the moment you know the joint distribution, then a classifier is just a point estimator or just a predictor. It's a mapping y hat from the feature space into the space of class labels. And then a potential measure of risk. The usual measure of risk would be the misclassification rate, the probability that you get your class wrong. And so for the moment, let us assume that the joint distribution is known. So W sub theta is the prior of class theta, and P sub theta is the conditional distribution of the feature vector given that you're in class theta. And let's suppose we have some density with respect to a dominating measure M. And then, of course, then you can compute posterior probabilities. So W theta of x is the probability that y belongs to class y is equal to theta, given that x is equal to lowercase x. And that's the usual formula. And then, of course, an optimal classifier is known to be the one which maximizes the posterior probability. And you don't need to normalize. You can just maximize prior probability times density. Okay. Now, instead of this, looking at this classifier, if you really consider the posterior distribution, the posterior weights, they carry, of course, additional information. For instance, 1 minus the maximum of your posterior probabilities, then is the probability, the conditional probability that your classifier is wrong. Okay, nevertheless, I would question that this posterior probability is really a measure of plausibility that the unknown class is equal to theta. And there are some reasons for this, and without any specific order. One thing, of course, is there is a strong dependence on the prior weights. And so your classifier would may change drastically if you change the prior weights. Another thing is that in very imbalanced situations, it may happen that some classes are just not treated well. That means conditional on being in a certain class theta, you may have a very high misclassification rate, which is maybe not what you want. And another thing is, in particular in medical studies, if you think about case control studies, it's possible to estimate the conditional distributions of your feature vector, but not the prior probabilities. So there are situations where you just have no idea about the prior W theta. And another thing is, which is maybe more an academic point, if you think about a situation where you have many classes, and some class distributions are very similar, then what would happen to your posterior probability is your posterior distribution would distribute the mass equally among those similar classes. And that would to some extent give you the wrong picture, and I think if you use the posterior probability as a measure of plausibility for a certain class, why should it be additive? Why should the plausibility measures add to 1? I think there's no convincing reason. And well, and of course, an important point is that this posterior probability in realistic settings may be difficult to estimate. Okay, and then if you think about what do people do if they have to classify in the difficult situation where it's not so easy to come to a conclusion, then people and experts often use the exclusion principle. So they have, if I have more than 2 possible answers, and if I don't have a clear idea, then I try to exclude some possibilities which are least plausible. And I think it would be interesting to use the same reasoning in classification. So my proposal is, and I'm not sure, maybe other people used this before, is to use p-values for the potential class memberships. And that means for each potential class theta, I'm aiming for a p-value function, p sub theta, from the feature space in the unit interval, which is a p-value in the classical sense that conditional on being in class theta, the probability that your p-value is less than or equal to alpha is at most alpha for any alpha between 0 and 1. And suppose you have such a collection of p-value functions, then you can compute a 1 minus alpha confidence prediction region for your class that is having observed x. Then you consider all classes as plausible which have a p-value greater than alpha. Okay, and then now there are of course several possible outcomes. The ideal case is that this prediction region just contains 1 parameter, just 1 class, so you have a unique classification with a certain confidence. That's nice. It may happen that you have that your prediction region contains 2 or more classes, but not all, and that means you have a non-unique classification, you have some evidence, so you can exclude some possibilities, but not all, but 1. The worst case, of course, is if all p-values are greater than alpha, then you have no idea what's going on, and it's also possible in some settings that your prediction region is empty, and that may indicate that you have a strange observation. Maybe you have observed a new class which you haven't been aware of. The point is, if you think about the first situation, even in situations where even the base optimal classifier has a substantial risk, that means even in situations which are intrinsically difficult, it is still possible to have unique classification with a given confidence, at least in a certain fraction of cases. And my impression is that if you look at the typical test examples from people working in classification, in particular in machine learning, in many examples, in particular where people really construct artificial distributions, the base classifier does extremely well. So that means if you knew a good classifier, you would do an excellent job. But I think in many real applications, the situation is different in the sense that it's really intrinsically difficult to distinguish classes. And in such situations, I think it's particularly useful to have a certain confidence measure. Okay, now you can just imitate the classical theory for optimal classification in terms of p-values. So let me assume that the densities are strictly positive, and then for a given class theta and a given test level alpha, I try to minimize the risk, which is just the probability that my p-value is greater than alpha. In other words, it's the probability that theta is viewed as plausible. Okay, so I mean, my aim is to have a small prediction region, as small as possible. So therefore, that's a natural measure of risk, depending on alpha. And of course, the constraint is that given that you are in the class theta, this probability should be at most alpha. Okay, so you can just apply classical name and Pearson lemma, and then you get an optimal p-value. And the optimal p-value let's see, is this? Okay, here it's. So the optimal p-value is very simple. You take the posterior probability of class theta, but you don't use it itself, but you transform it. So you consider the distribution of the posterior probability under class, conditional on class theta. And so you transform this number, which is already between 0 and 1, again to the unit interval, and that gives you an optimal p-value. And this works well if the distribution of this posterior probability is continuous. Okay, so one important thing is to see the difference to the classical to the classifier is you may in this definition you may replace this posterior probability with this quantity. So I got rid of the weight W theta essentially. So in the enumerator I only have the density F sub theta, and in the denominator I have a weighted sum of the other densities, and the weights depend only on the prior weights of the other classes. So that means if you want to decide whether class theta is plausible or not, the prior probability W theta itself is irrelevant. Okay, so that's an important difference to the usual Bayes classifier. Okay, and now this condition, actually that's a point where Axel Munk had something interesting to say. There is a continuity of this posterior probability is closely related to identifiability questions in finite mixture models. So that's a very interesting topic by itself. And roughly speaking, this continuity assumption is related to a property which we call local identifiability. And in particular, it's always satisfied if you have pairwise different Gaussian distributions. Okay, so here's an example. I have 3 classes, equal prior weights, and it's heteroscedastic Gaussian model, bivariate. So you will see some data in a minute. And heteroscedastic means I have 2 identical covariance matrices and one which is smaller in a Löwner sense. And so here's a typical situation with, I think, 100 data points per group. And now if you think about the Bayes optimal p-values, so these are the p-values for class 1. So the color or the gray coding is 1 is corresponds, black corresponds to 1 and white corresponds to 0. Okay, so that means here class 1 is very plausible, and here it is not plausible at all. Now for this, that was the first class, red. The second class is here, down here, and the third class is that's the p-value function for the third class. And then if you think about these prediction regions, in this situation, if you take alpha equal to 5%, so you have 95% prediction regions, you have almost everywhere unique classification. So here red means these points are uniquely classified as 1. The green points are uniquely classified as class 2, and here uniquely as class 3. You have a certain strip here where points are not classified to any class. So this is a strip of very low probability under each distribution. And here you have this yellow region where your decision is not unique, but you say classes 1 and 2 are plausible, but 3 is not. And if you would increase alpha to 10%, then you would have only unique classification or no class membership at all. Now here's the same situation, but with the centers of the distribution less far apart. And so the p-value functions look still similar, but now the prediction regions change. So now you have a region here where you say it's class 2 or 3 here again, and here it's almost invisible. But here's a region of points where you say, oh no, not in this example. One. Now if you decrease to, oh no, sorry, I was wrong. here, the white region means these are points where you don't have, you say any of the three classes is possible, okay? Okay, and that's again, if you increase alpha, then the ambivalent regions become smaller. Okay, now that's only for the unrealistic setting that you know everything about the joint distribution. So now let's consider training data. So suppose the joint distribution is unknown and we have independent, for simplicity, identically distributed observations. So I have n training observations, which I denote by script D, and I have one future observation where Y is not observed. And so now I'm looking for p-values which depend on the training data and on the new feature vector x. Okay, so the first argument is still x, and there's a second argument just standing for the whole training data. Now if you think about what property would you like to use, would you like to impose, there is one natural property that is single-use validity, and these phrases are borrowed from calibration theory. So in calibration you think about single-use and multiple-use validity. So single-use validity means the probability that your p-value for class theta is less than alpha, given that y belongs to theta is less than or equal to alpha. So the point is, in this probability, there is the randomness in x, but also in the training data is included. Okay, so you have the randomness in both parts. And but if you think about, I would like to use my training data to classify many future observations, then you should condition on your training data as well. And so that would be the approximate, or the multiple use validity would be about the probability that your p-value is less than or equal to alpha, given that your new class y is equal to theta, and conditional on your training data. And it's not possible to control this perfectly, but at least in some situations you can achieve that this is less than or equal to alpha plus a small remainder term going to 0 as n goes to infinity. Okay, so here's a simple example which you find in the monograph of McLachlan. It's about p-values, but these p-values have not been designed for classification. It was more coming from quality control, but nevertheless it's good to illustrate the concept. So we have a standard homoscedastic Gaussian model. So we have a multivariate, a q-variate normal distribution, a common covariance matrix, and different mean vectors. Now you consider the standard group-wise averages as the estimators of the mu, and you consider the standard estimator of the covariance matrix. And then, if you want to decide whether a new feature vector x is, whether class theta is plausible for x, you consider the Mahalanobis distance between x and the estimated center of class theta. And then it's well known that if you are in class theta, then this Mahalanobis distance, properly standardized, has a F distribution. So you come up with a p-value. So your p-value can be easily computed using the standardized Mahalanobis distance and the F distribution function. Okay, and yeah, let me illustrate this, because that's a nice data example. We have been consulting a small company which built electronic noses, and an electronic nose is essentially an array of at that time 10 different electrochemical sensors, and so you try to smell something. Okay, so the raw data is just the signal, the 10 different sensor signals. Then if you do a standardization, if you're not interested in concentrations but only interested in classification, then you should standardize it somehow to a 9-dimensional vector. Okay. Now this company, they were not allowed to give us real data sets from their customers, so they produced a toy data set themselves. And since all of them have been heavy smokers at that time, they provided us a data set. They considered 12 different brands of cigarettes, and they made measurements with a sensor array and 9 measurements per group. Okay, so you have 12 different classes, and you have 9 measurements per group. And then if you use these p-values, which I just described, by these typicality indices, and then now each row here corresponds to an observation. And what you see, these rectangles are just the p-values. Okay, so for each observation, you see 12 different p-values, and the area of the rectangle is proportional to the number. Okay, so you see all observations in class 1 have a high p-value for class 1 and very small p-values for the other classes. The same is true for class 2, class 3 again, class 4 is fine, class 5. Class 6, well, in class 6 it's not unique. There seems to be a strong association between, or similarity between classes 6 and 7. And then class 8 has a certain overlap with 2 other classes, and so on. So you see, you can, in case of small training data sets, you can easily visualize your results. And by the way, these have been computed using cross-validation. So I took one observation out of my training data set, computed the p-value with a reduced training data set, and now I visualize this. Okay? Now this similarity between classes 6 and 7, that was funny because later on, when I told them that I had difficulties distinguishing these two classes, I have difficulties distinguishing these two classes, they told me, well, classes 6 and 7 have been identical. It was just I think two different packages, but the same brand. So I was happy that I did not come up with a perfect solution. And the funny thing was that a colleague of mine who was very fond in neural nets, he analyzed the same data, and his classifier did perfect, even with cross-validation. Okay. So we were wondering and discussing what was going on. If you look at the p-values again, maybe you see something which is strange. Do you see any pattern? Do you see some pattern? What?
Always non-unique?
Well, that's not the only point. No, here it's unique, but here you see a pattern, although it's unique. You see? Yeah. You see groups of 3, right? You see. Essentially, you have always three similar results. And the point is, and in fact, they did not give us 9 measurements. They only made 3 measurements with 3 repeated measurements. Okay, so they thought this is not a big thing. But the point is, of course, the guy with the neural network, I mean, if you do leaving one out cross-validation, you take one out observation, you take out one observation, but you still have 2 siblings. Okay, so, and then if you overfit, then you, of course, you get perfect results. Okay. So, having learned that there's a block effect and we should reduce the data, then we came up with this. And so again, you have a little more non-uniqueness, but nevertheless, you hardly have. If you could consider the corresponding prediction regions, the worst thing you can get is you have 4 possible classes out of 12. Sometimes you have uniqueness, and sometimes you have just 2. And I'm not claiming that these particular p-values are particularly useful for this question, just to illustrate the concept. Okay, so it's possible to refine it because Mahler-Nobis distance, this test statistic I was considering, does not take into account the information from the other classes. So you only compare x with a certain center mu theta without taking into account where the other centers are. And so this could be refined. But now let me talk about non-parametric p-values. And the idea is very simple. I'm performing permutation tests conditional on the class memberships. Okay, so now I'm considering the class labels y sub 1 up to y sub n as fixed, or I condition on them. And then I rearrange my training data for simplicity. So I'm only focusing on one particular class theta. Just for illustration, I rearrange my training data such that the first m sub theta observations are the observations coming from class theta. And then the simple observation is if my new class label is equal to theta, then this tuple of new feature vector and these training feature vectors is exchangeable. Okay, that's the only thing you have to know. And so you take, if you take some test statistic designed such that small values of this test statistic give evidence against membership y equal to theta. Okay, and it's important that this test statistic is symmetric in my training data from one group. Okay, and now I take this test statistic, this value, and I compare it with a permuted value. So because of symmetry, I don't have to take all permutations, but I just replace one training observation with a new, or I exchange one training observation and the new observation. Okay, so here I exchanged x and x1, here I exchanged x and x2, and so on. So I have n sub theta artificial values, and then you just compute Monte Carlo p-value as usual. You take 1 plus the number of permuted samples where your test statistic was smaller or equal to t sub theta divided by 1 plus n sub 1 plus group size. Okay? And the point is that this test statistic may be any test statistic. And so, for instance, you may be ambitious and try to estimate the posterior probability of class theta given x. So you may try to imitate this using a plug-in estimator for parametric models, using a kernel density estimator, nearest neighbor density estimator, or whatever. Or you could say, well, I use some surrogate, and maybe related to the setting that Sarah van der Geer was describing, if you think just of two classes, then you could try to design a test statistic which is, well, t sub 1 is the same as minus t sub 2, and it's just a linear combination of certain basis functions. And these factors b hat, beta, j hat are estimated from your training data using linear discriminant analysis, logistic regression, penalized logistic regression, or whatever. And okay, so let me just continue this very small example. One, if you use the plug-in rule for the homoscedastic Gaussian noise model, although it is not correct, the model, but still you end up with reasonable acceptance regions. And here would be the same thing with the 100 nearest neighbor method. And okay, so and also we looked at the quality of these compared to the base optimal classifier, and they're not too bad. Now you can imagine that the procedure, this permutation procedure, is rather computer intensive, depending on what type of test statistic or what classifier you have in the background. There is a possible shortcut which is not advisable, but which is used implicitly in some software. Is that you just ignore the dependence of your test statistic on the training data. That means you construct your test statistic, and then you just plug in your new observation and your training observations, and just ignore this. And implicitly, this is done by any standard statistics software like SAS or SPSS using producing receiver operating characteristic curves for classification. Okay, that's implicitly used, and I think it's a bad idea because it gives you very biased results. Another shortcut which is valid is the following. If you think about your test statistic as, okay, you take your training data to learn something about the underlying distribution, and then you plug in a new observation, just do the following. You take your new feature vector and just put it to the group of training observations from group theta, and then use this slightly modified test statistic, because now you really may just plug in your new observation and your training observations. Okay, and that wouldn't violate the validity. And of course, some robustness of your test statistic would be helpful. It's maybe not that necessary, but I mean, you add one observation, which is possibly from a different distribution. So there should be no drastic difference between this test statistic and this test statistic. Okay, so here's another example. So that was a surgeon in Lübeck at the University hospital. He was building up a database for quality management, and he gave to us a specific data set where we had patients undergoing a certain type of heart surgery, and for each patient we had a vector of 21 covariables describing the patient himself in terms of age, weight, gender, and whatever, and also the conditions of the surgery. For instance, was it an emergency or not? Was the surgeon experienced or not, and stuff like that. And the outcome was mortality after this surgery, so sticking to the class labels 1 to L, so 1 is alive and 2 is died. And so in this data set, which comprised a little more than 20,000 observations, the prevalence of dying was 3.1%. Okay. So now the obvious question is, can you, I mean, these 21 covariables are available right after the surgery, and then the question is, can you predict mortality based on these 21 covariables, which would be useful for the hospital to say, well, certain patients should go immediately to an intensive care unit or just go to the usual unit or not. Okay, so I extracted training data from this data set. I took all cases. So I took, in this set of 20-something thousand patients, I took all 662 people who really died. And then I matched, did a little stratification for gender, and then I took 3 times as many patients who survived. And I used the plug-in rule from the logistic regression with the shortcut 2 I just mentioned. And so here's the estimated distribution of my prediction region. So the prediction region, first of all, the question is, with which probability does it contain the class 1 if y is in fact equal to 1? So that was in 95% of all cases. And with 22% probability, it contains also 2. And here's more precisely the pattern. So in 77.8% of all cases from survivors, you would classify them correctly as and uniquely as survivor. And 5%, exactly 5%, would be classified misclassified as non-survivor. And in 17.2% you would have no clear decision. Okay, and the group of non-survivors was a little more difficult to handle, in the sense that you have only 64.4% unique classifications, and you have 30.7% cases where you don't know, where you have no clear decision. Okay, but nevertheless, this is already helpful. I mean, at least in 77.8% in the one group and in 64% in the other group, to have a clear decision with a certain confidence. Now, maybe 5% would be a little too high in this setting. So if you go down to 1%, then still you have a little more than half of the patients who survived would have been classified correctly to this category, and at least 30.2% of the non-survivors would have been identified as non-survivors. But okay, now we have almost 70% where you don't know. Okay, here are the corresponding estimated receiving operator characteristics. So what I'm plotting here is, on the horizontal axis is always the unit interval. It's alpha between 0 and 1. And here's the probability that your p-value is, for a certain class, is less than or equal to the given alpha. Okay, so these are just the traditional ROC curves, but now computed with a cross-validation scheme, which should be more reliable than the traditional ROC curves. Okay. So. Okay, so here's some, yeah, I think I have time for this. Here's some classical asymptotic theory within the classical framework. Classical framework means everything stays fixed, but n goes to infinity. So suppose that my test statistic, no matter how I designed it, converges in probability as n goes to infinity to a fixed test statistic depending only on x, okay? And obviously, if you use some plug-in rule for parametric model or so, this is very easy to check this this condition. And in addition, suppose that the distribution of this test statistic is continuous, and then you can conclude that for arbitrary classes, class labels beta and arbitrary theta, the probability that that our permutation type p-value is greater than alpha, given that the true class is B and given the training data, this conditional probability converges in probability to this limiting probability here. So you have a limiting p-value p theta naught, and this is just defined with a limiting test statistic as the base optimal p-value was defined with a posterior weight. Okay, very simple. And in addition, in particular, you can conclude that the risk of our estimators as a random variable conditional on the training data converges in probability to the risk of the limiting p-value. And if you take any cross-validation type estimators of these probabilities, these are consistent, and also you end up with that these conditions are all satisfied with the limiting p-value being the base optimal p-value if you use the nearest neighbor method with a growing number of nearest neighbors but slower than the sample size. Okay, so that's all the classical zero order asymptotic theory. Okay, now let me briefly comment on high dimensional settings, and what I'm planning to do now is, well, in high dimensional settings, an obvious thing is to use regularization, and for instance, if you think of two classes for simplicity, as I just mentioned, so I'm looking for test statistics or for discriminant functions, you should say, of the form T1 is minus T2, and it's just an estimated linear combination of certain base functions, and your parameter b hat, beta hat minimizes a certain empirical risk with a certain loss function plus some penalty factor, and this may be an L1 norm, L2 norm, or whatever. Okay, and now what are in my opinion, the most important questions is one, of course, how should you choose lambda in a data-driven way, having in mind that you're not interested in classification or in regression, but in p-values for classification. What recipe for choosing lambda would be appropriate here? And then one property is stability. Note, it's about are you interested in single-use performance or in multiple-use performance? And in the classical framework I was describing, asymptotically, both things are identical. So that means the risk conditional on your training data, I mean the probability that your p-value is greater alpha, given the training data and given the class of the new observation, is approximately equal to this unconditional probability here, or I mean where the randomness in the training data has been averaged out. And in addition, if you use some cross-validation scheme to estimate this, and this was consistent. So in the classical setting, we know that these three probabilities are all asymptotically the same. And I think then, at least if you use some regularization, some appropriate version of regularization, even in high-dimensional settings, this should be correct. But I don't know yet. And it's also not clear to me what is the role of sparsity in this business here. Okay, here's a very little simulation experiment. So yesterday I was joking. I said I have to add some dimension to my talk. So here is what I did last night. We have two classes. We have 200 observations per class, and I forgot to mention the dimension. The dimension is 100. Okay, the dimension is 100, and I have just a very simple homoscedastic Gaussian situation, and only one coordinate, the very first coordinate, is really relevant, and I have plus or minus 2 depending on classes. Okay, and take logistic regression with a penalty lambda times L1 norm of B hat. And okay, so here are the ROC curves for lambda essentially equal to 0. And so if I mean B equal to 1 and B and theta equal to 1, then you should have the identity. That's okay. So the blue curves are estimated based on my procedure, the estimated ROC curves. And the magenta line, this would be the base optima. For this particular situation, this would be the best possible ROC curve. Okay, so you see there's a certain gap here. And now if you do Lasso, and I have no data-driven choice, I just took 5, and you can ask me in the tea break why 5. And now you see that the estimated direction of for my discriminant function is much better. The first component after normalization should be 1, and now it's at least 0.95 something. And also you see that now the performance got much closer to the best possible performance. Okay. And then finally, I applied the same to the data example, the hospital data, and which is not high dimension in the sense that the ratio of observations, number of observations to dimension, which is a few thousand to 21, is large. But nevertheless, I was wondering what happens to this estimated distribution. So here's again the same numbers as before without penalization. So I have this 54.8% unique classification for class 1, and I have 30.2% for class 2. If you do regularization with lambda equal to 5, and I admit I played around a little, and this was essentially, well, 7 was a little better, 8 was a little worse, so I just stuck to lambda equal to 5. At least you could increase. For class 1, things got a little better. So for class 1, you could increase by 3% the unique classification, and you could decrease the non-unique cases by 3%. And in class 2, essentially nothing happens. So it got slightly worse, but it was amounted just to one case. Okay. So, well, to conclude my presentation, I think first of all, p-values are an interesting concept for classification, and another point is that even for computer-intensive and fancy classifiers for high-dimensional settings, it would be worthwhile to try this concept on these. Thank you very much.
Seen these ideas before, but instead of the regularization, a dimension reduction for high dimension might actually be another alternative, which gets you back either to the sparsity or the dimension reduction,
well,
what you want to call it, because clearly your very early ideas suggest that you're not actually doing much better
with what?
You're not doing any better when you have a regularization.
Well, in the example before I did, and in this example I think it's just, I have really lots of observations here and only 21 dimensions. So I think that's a setting where regularization is not that important anymore. Yeah, so, and I mean, I was using the L1, the Lasso type penalty, so it does do some dimension reduction automatically. Okay, so it reduced the number of relevant components from 21 to I think 14 or so. It was not drastic, the effect, and those components which disappeared have had very small and non-significant components before. So I think in this example, I think in terms of model fit, it's a nice example. I think logistic regression is doing very well. And again, our neural network colleague, he tried here also, and he didn't do any better. So I think classical logistic regression was fine for this example. Yeah, Peter.
Very nice. There may be some connection with this notion of margin in classification, at least as formulated by Sasha. I'm not sure that he's here. That, there's a population notion of margin. In other words, how easy is it to separate the two classes? And I think that's connected with the distribution of likely ratio. There's some connection. Don't see it precisely, but it might be worth looking at that.
Yeah, thank you. Yeah.
Okay, no, see. Does that seem reasonable, Reno?
And not taking so.
Yeah.
So I was interested. I hadn't seen your shortcut where you.
Yeah.
So it's sort of what you're doing is the one you usually leave out. You're actually using its y as well. So you're using its data as well. So you must. It seems intuitively you must lose a little here, like power or something. How does this do you understand how this compares to
If
rerunning the whole thing?
Yeah. I can only tell you what happens in the simple Gaussian setting, and what happens is if you're in the central part of the distributions, essentially nothing happens. Although the test statistics are not robust because they are based on sample averages and sample covariances. But if you go far out, then you see a difference. Because then the point is if x is really, if this x is far out, is far away from the training data, then this observation of course spoils your estimators of centers and of covariance. But the point is that happens far out of the bulk of the distribution, of the main part of the distribution. So if you think that your model is correct in the sense that also the new observation comes from one of these L distributions, then the effect of adding the observation beforehand to one of the groups that is not very strong. But I mean, you're right. So that's the point here. So some robustness would be helpful. So I would like to replace the usual sample mean and sample covariance by some slightly robust version.
But you're getting the distribution by permutation, right? And
Right. Yeah.
So there's no robustness in the alpha level.
No. I'm talking about
separate.
robustness. Yeah, I'm talking about robustness in a very naive sense of what is going on here. What is the difference between this and that?
Any other questions? Okay, if not, let's thank you.